speaker is Tim Rogers from Bath. Okay, then welcome.
Okay, thanks very much for having me. I'm having an absolutely great time. So scientifically, I'm really enjoying the talks, and Rio is just a lovely place. So I'm really glad to be here. Okay, so I'm going to tell you something about epidemiology and epidemic spread on networks. It's going to be completely non-rigorous. There are things to prove, but I just haven't chosen to prove them in this case, mainly because I'm looking to try and apply these ideas to real data, and the people who care about that don't so much care about proving things, right? So I'm going to tell you about two questions you could ask about the spread of a disease on a network, and they're very similar, but they're not exactly the same. So one is, if you seed a disease somewhere in a social network, what's the chance that it spreads and manages to cause a major outbreak? And then you can ask the reverse question, which is that if I think that somewhere in the world there is some deadly disease that might be spreading towards me, what's the probability that I get sick? So these are sort of dual questions, but they don't have the same answer, right? The second one, it turns out, is easier to study, so I'm going to start with that, and I'm going to call it vulnerability. So this is your risk to an epidemic that might be spreading somewhere else in a network. Okay, so the model I'm going to work with is a simple SIR model, which most people have heard of, so I'll rattle through this. So the idea is that you have three states. You can be susceptible, infective, or recovered. These light blue guys are susceptible, so they might get the disease. And then you start it off with one initial infected individual, and I'll color them red. So that's they've got the disease, and then that can spread. And it spreads over the edges in the network. And this is a time-based model. I care about the passage of time. And so this spread happens with a probability beta dt per unit time dt, right? So this is like a Poisson rate with which it makes this jump, okay? Infective nodes can then recover, and recovery needn't be memoryless like the infection process was. I assume that the recovery time is distributed according to some PDF, right? So there's some distribution of how long you stay sick for, right? So another infection might take place, maybe another recovery, and now we're in a situation where even though there are susceptible and infective individuals still around, because there's no links between them, nothing more can happen. So the disease is stuck now, and the only thing that can happen is this guy recovers, and we reach a final state where there are no infectives left, there is only susceptibles and recovered, right? So for the question of vulnerability, it turns out what matters in some broad sense is just one number, right? And we call this the transmissibility. So it's the probability of catching the disease directly from your neighbor. So you can calculate this. You just integrate over, you need to know how long your neighbor was sick for, and then what's the probability that you got that little exponential, what the exponential clock for the disease spreading thing rang before your neighbor recovered, right? So if this is a small number, then it means that you've got a low probability of getting sick, and so the disease is probably going to die out. If it's a large number, then it's probably going to spread quite well. Okay. So the question we want to answer is, who is most likely to get infected? Who is at risk? You can imagine with a different network topology, different people might be more or less at risk from a disease spreading. Okay. So an example, here's some little tiny network that I cooked up. And I'm going to seed it with an infection here, and there's a 90% transmission probability. So if I were to run a simulation of this, I get a different result every time, right? It's random, but a typical one might have it spreading quite quickly, and then the recovery comes along. And maybe you end up with some state like this, where most people died, but there's a couple of guys who managed just by chance to avoid the infection. But the infection spread well, and most people got sick. So just to wake everybody up, after lunch, we're going to have a quiz. It's compulsory to take part, right? Usually nobody votes, right? I want you to have a look at this network and this seed node for the disease, and I'd like you to decide whether you think node A or node B is more at risk of catching this disease, okay? I'm going to give you a couple of seconds to think, and then you have to vote. All right, so put your hand up if you think A is more likely to get sick. All the way up, all the way up. Okay, put your hand up if you think B. Okay, that's pretty evenly split, actually. So I think the answer is B. So can a brave person who voted B tell me why? Yeah? No, it's closer. It's closer, right? So you're right. You're exactly right. So B is 3 steps away. So you only need to have 3 transmission events for B to get sick, right? Whereas A is 4, okay? So really simple, right? Let's try again. So I'm now looking at this guy. So this guy is now the same distance as A. So that previous argument doesn't work anymore. So study this for another few seconds, and we'll vote again who you think is more at risk. Okay, hands up if you think A is more at risk. Hands up if you think B. Somebody different who chose B, tell me why. Okay, interesting. Okay, all right. That's not the right answer. It's a right answer. I'll get to that. So here I claim that B is more vulnerable because it has more neighbors, right? It's more simple than that, okay? So this is a highly infected disease, so lots of people are likely to get sick, and every additional neighbor you have is another chance to get sick, right? So Paul has unfortunately skipped 3 slides ahead, so I'm going to have to rattle through this. So you spoke about the number of paths, right? And that actually matters when the transmission probability is lower. So if you have a slightly weaker disease that doesn't spread so well, so a typical outbreak is much smaller, so then we're going to vote again, but Paul's ruined it. Well, no, we can still do it, right? So I'm going to ask you the same transmission probability. Actually, there's no point. I've given it away, right? So actually, it's swapped. So for a lower transmission probability, it's path counting that matters rather than number of neighbors. Right? So these are things that you can get from just checking simulations and whatever, but I want a theory to say why this should be the case. Okay, so this is what I'm going to try and develop now. And I'm going to use a trick from statistical physics called the cavity method, and it's more or less just recursion equations, okay? So the idea is I'm going to write VI for the probability that node I gets infected eventually in this process. And I can write an expression for VI as a function of what I call VJI, which is the probability of a node J being infected in a network where I was removed, right? So the justification is as follows. So what's the chance I get sick? Well, that's 1 minus the chance that I don't get sick. And how could I fail to get sick? Well, for me to fail to get sick, I need each of my friends to fail to spread it to me. And those are independent events. And so I take 1 minus the chance of spreading. And then spreading is T for transmission times the chance that they got sick, but not through me, right? So all this is basically saying is that if you're going to get sick, you need one of your friends to have caught it from somebody else. And then they get to transmit it to you. So far I haven't achieved anything, right? Because I've got n variables here, and I've got twice the number of edges is the number of variables I've got on this side, so I've just made the problem worse. But then you do this kind of hand-wavy thing that can be justified for the limit of large networks that have a tree-like structure, so things like Erdős-Renyi or the configuration model or whatever. Then you can do the same trick once more and find a closed system of equations. So we say, so I wrote my vulnerability as a function of the chance of my friends getting sick but not involving me, and I want to now have an expression for that. Well, I need to think of their next neighbors, and the trick is that really I should here be talking about somebody else getting sick without J and also without I. But I'm just going to assume that probably short loops are sufficiently rare that correlations only pass through the central node, and so if I've removed J, I've probably removed the shortest path from I to L, so I can not include I there. So this is now a closed system of equations that hopefully provides a good approximation to the probability of a node catching the disease in this epidemic model. And in fact, you can show that actually the solution is an upper bound. So it is useful for something, right? Okay, but it's a tight upper bound, or generally. Okay. So here's the procedure. So if you have this question, you say, I've got some disease and I want to know how risky it is. Well, I compute the transmissibility. It's just this integral. And then I solve this system of equations, and then I plug that in here to get these vulnerabilities, right? But this system here, there's twice the number of edges is the number of variables, and they're all nonlinear. So this is a mess, okay? This is really hard to solve. And so numerical solution is going to be the only option. Okay. So to do the numerical work well, I'm going to show you another way of packaging up these equations that uses a dual graph to the original underlying graph, okay? And that dual is called the Hashimoto graph. And the idea is it tracks non-backtracking paths in the underlying network. So I start with some graph, and then I make a new one whose edges are ordered pairs of vertices from the previous one. No, sorry, whose nodes are ordered pairs of edges from the previous, and whose edges, so you join two pairs of ordered nodes if you can do a walk in that direction. So if you're struggling with that, I'll give you a simple example. So here I've got a 4-node network. So what does a Hashimoto graph look like? So this isn't going to be a quiz question because it looks like this, right? It's horrible. But basically, what's happening here is that every edge, every red edge in the underlying graph sprouts 2 nodes for the 2 directions that it could be traversed. So I do that for every edge. And then I join them up if it's possible to traverse one and then the other without turning around. Okay. So this is also known as a non-backtracking operator. So with that, armed with that dual graph, I can write down a simple map for which solving the cavity equations means just finding a fixed point of the map. And the map involves taking a product over edges in this dual cavity Hashimoto graph. Okay. And it turns out that you can just iterate this. So this is a contraction. So you can actually solve this whole system really quickly. In the computer, you just keep iterating. So I've done this for a random graph. So I generated a configuration model network with nodes of degrees 3 and 5. And then I solved this system of equations by iteration. And I'm plotting here, so I'm varying beta, the transmission strength of the disease. And each gray curve is the probability, is the vulnerability of a node. So it's a probability that that node got infected in an outbreak that was started somewhere else in the network. And I've highlighted 2 ones in particular that do this phenomenon. These are like the A and the B in the quiz. So the green circles and the blue diamonds, so I should say the curves come from the theory and the shapes come from simulations. And they switch over, right? So the green guy is more likely to get sick than the blue guy when the disease is quite weak. But if the disease is quite strong, then he's less likely to get sick. So there's this order changes as you change the strength of the transmission of the disease. So what I'd like to do is I'd like to understand why that happens, right? So I'd like to know what's happening up here. Also, you've got this phenomenon, right? This is a percolation type thing, right? That it's 0 everywhere, and then suddenly, boom, they all come out and something different happens. So I'd like to know what that point is and how is this ranking decided here and how is it decided up here, okay? And both of those questions are simple enough that a linear theory will do. So what I'm really asking is, so if I want to know when is an outbreak going to happen, so I claim that there was this, this equation that you could iterate to find the probabilities of getting sick. And so what I'm really asking is when is 0 a stable solution of that, right? Okay, so I write it down, and then I just do the standard thing. I do linear stability analysis, so I differentiate with respect to one of the variables and check what this is, and then evaluate that at 0. And I find that the Jacobian for the point 0 in this system is just t times the adjacency matrix of this Hashimoto graph that I told you about. So the top eigenvalue in particular encodes the epidemic threshold for this network. Okay? It also encodes some information about the ranking, the relative ranking of the nodes. So if I now think about differentiating with respect to t, so I'm making a small change to the properties of the disease, well, I can go ahead and do that. And close to criticality, I know that most of the vulnerabilities are very small, so again, a linear theory will do. And what I find is the eigenvector-eigenvalue equation, again, from this Hashimoto matrix. So the top eigenvalue tells you how strong the disease has to be to spread, and the corresponding eigenvector tells you the relative ranking of the nodes in terms of how at risk they are in the network. At the other end, so when transmission is very strong, so I'm at completely the other end, v is very close to 1, so I end up with a completely different asymptotic. And in fact, I'm rushing, sorry, this is usually a longer talk. But in fact, it turns out that the linear theory won't ever do. You have to do, the first non-zero derivative occurs after you've done as many derivatives as there are neighbors of that node. So the vulnerability ranking in strongly infectious diseases depends on degree. So what I'm really saying up here is that these curves, they all leave 0 as straight lines, and the slope is determined by the eigenvector from this matrix. Up here, they all approach 1 as a polynomial power, and the power is the degree. Right? Okay. So that's a summary for vulnerability. I'm now going to talk a little bit about risk, which is this opposite question of if I seed an infection somewhere, how likely is it to spread? So that's exactly what I was saying. So suppose this guy comes first. I mean, how likely is he to cause a big outbreak? So there's a little spread. Now I have a problem, right? Because these two nodes are exposed to a single source of randomness, which is the lifetime of the infectious period of this guy. So if this node stays sick for a really long time, then with high probability, both of these guys are going to get sick. Whereas if he gets better really quickly, then with high probability, neither of them are going to get sick. So their fate is quite strongly correlated. What that means is that I have to, instead of just being able to talk about transmission between pairs, I need to think about transmission to a subset of the neighbors. So for every possible subset of the neighbors of a node, I can ask, what's the chance that I infect those guys and nobody else? So this is some more complicated integral, which then allows me to compute the risk of the spread of this disease. So this is a bit like a branching process. And in fact, there is a map from this model to typed branching processes. So I'm asking, so what's the chance that I cause, if I seed node I, that he causes a major outbreak? Well, that's 1 minus the chance that he fails. And failure is determined by, there's lots of ways you can fail. So I sum over every possible set of his neighbors that he could have transmitted to, and then ask that none of them succeeded. So 1 minus RJI. Is that's not clear to me anymore. You'll have to take this as fact, okay? That's interesting. Okay, after the talk, I will figure this out, right? Okay. This bound allows me, if I believe it anymore, allows me to move away from having to talk about subsets and push it back into discussion just of individual edges again. The trade-off is that previously I just had a single number t that was this chance of a one-off transmission. Now I care about this sequence of numbers tn, which involves 1 minus e to the minus beta to the power n integrated over the lifetime. So I really care about the detail of the lifetime distribution. So different diseases, each with the same T, so the same transmissibility, will be more or less likely to actually cause outbreaks dependent on their lifetime distribution. Okay. So here are the final set of equations. So again, they're the same size as the previous ones. They're just more complicated because I have to sum over all the possible subsets. All right, another quiz. So I just told you that for vulnerability, so for my chance of getting sick, all that mattered was this one number, and that the disease lifetime distribution wasn't so important, it was just this one number. Keeping that number fixed, but varying the properties of the disease lifetime distribution, can we say which choice of disease lifetime distribution is most likely to cause an outbreak? So if you were engineering a chemical weapon or something, I could think of a nicer analogy, whatever. What would you choose for the duration of the transmissible period? Would you like to have a memoryless one, sort of exponential, constant chance of getting better? Would you have a heavy-tailed one, so most things recover very quickly, but some of them stay sick for ages and ages? Or would you go for something sharply peaked, like the yellow? Okay. So who votes for A? You have to vote. Which of these is most risky? Okay, anyone vote for A? One person. Anyone vote for B? Two? Hi, I want to see. Okay, C? This is really good, right? C is the right answer, and you're the first audience. So can someone tell me why C? Who voted for C and has a good reason? There's a maths reason and there's a biology reason. Or was it just a hunch? Okay, so the maths reason is Jensen's inequality, but I don't expect any of you will have done that. So the biology reason is, you can actually think about this, right? So most human diseases have a typical period, right? It's about 10 days that you're transmissible for. And the reason is that you want, as a disease, you want to guard against the possibility of going extinct very quickly. So you don't want to kill your host very fast, right? So any mass in the probability distribution down here is really bad news. So you need to kill this stuff off, and the only way you can do that is by balancing at the other end as well. Okay. But mathematically, it's Jensen's inequality. So you just push this n outside of the integral. So you have this expression. And so that gives me upper and lower bounds for the risk associated to a particular possible transmission. So one way to illustrate this, so here I've plotted risk, and risk is in purple and vulnerability in green, as a function of, so I'm using Weibull distributed lifetimes, which has this funny form, but all you really need to know is it interpolates between heavy-tailed, memoryless, and a delta function. And the purple line, this is the risk, so the chance of causing an outbreak, is always below the green. So you're always more likely to be caught in an outbreak than you are to start one. But they match when you have a delta function, and they're most apart when you have a heavy tail. Okay. You can try and do the same thing as I showed you before about ranking the nodes according to which seed is the most likely to cause a big spread in the network. And there you get an absolute mess. So I don't even begin to know how to understand what's happening here. So I'm doing the same thing. I'm varying that parameter for disease lifetime. So this is like the memory of the disease process. So this is going from heavy-tailed to memoryless to Dirac delta. And I'm ranking the nodes according to how risky they are. So which one is the best seed. And you can see that this ranking is in no way preserved. There's this strange feature that memoryless seems to be either a maximum or a minimum for most nodes, but you can't tell which one it's going to be. And they cross over each other. You've got this spaghetti. So again, the ranking of where should you seed your disease depends very strongly on the characteristics of the disease, but in a way that I find completely non-obvious. So I have no idea for any theory for this. So if anybody has any good ideas, I'd love to hear them. So that's it, basically. So here's a summary. So I'm at least confused about epidemics on networks, but this is good because it means there's more papers to write. I claim that this cavity method computes very good approximations to these quantities if you run simulations on a network versus solving these iteration equations. And the cartoon I use to try and understand these two different versions is, I think of upstream and downstream. So upstream being this kind of branching process of, do I manage to cause an outbreak? And downstream being, how many routes are there for the disease to reach me if this is the guy I'm worried about? Anyway, that'll do, I think. So thanks very much.
Okay.